The next two wave behaviors of light we're going to look at is diffraction and interference. So first of all, diffraction. Diffraction is basically what happens with waves. When waves get past an obstacle, they bend, they spread out. So an easy example to understand of this is if you stand behind a tree and someone yells at you, you can still hear them, right? It's not like because you're behind the tree and you're not in line of sight of them, that doesn't mean you can't hear them. That's because the sound as it goes out from the person's mouth, it doesn't travel in a perfectly straight line, it's going to bend. So when it goes past the tree, part of that sound wave is going to bend around it and go to your ears. So the same thing happens with light. And here's a basic way that you can look at this. So let's say these are plane waves. When I say plane waves, I mean straight line waves, and they're moving to the right. So I have plane waves moving, and they're going to hit this little slit. So this is a barrier, and in the middle of the barrier there's a single slit. So what happens is, as the light goes through there, or any wave, but in this unit we're mostly speaking about light, the wave is not going to continue just in a plane, because one little part gets through and it's going to bend like this. And you can actually see this happen if you do this with water. If you make some waves in water and then let it go through a little hole, it'll actually make this pattern. So this isn't a theorized pattern, this is something that's actually been observed, and we'll try to look at some of these a little bit in class with some of the materials that we have. So the question is, why does this happen? And what happened is there's a scientist named Huygens, and Huygens actually had a good explanation that explained this, and so he gets the principle explaining diffraction named after him, which is kind of groovy. So this is Huygens' principle. Basically, that every little point along a wave can be considered a tiny source of waves. They call those wavelets. Those are like baby waves. So those baby waves are moving out, and all of those baby waves together create a wave front that continues. So here's what happens with my plane wave, my line wave. So it's moving to the right, but the orange line is the actual wave. So imagine there are an infinite number of little points along the orange line there. What happens is that each little point along that line will behave in that semicircular path that we saw on the last slide. It's a little hard to draw infinite on this, so I drew 4. That's kind of close. And so let's say we have all these semicircular paths, and if I were to draw more in between, halfway in between, you should see that those would start to overlap, and they overlapped in such a way that the top of those waves form their own new little crest. And so that's how the wave propagates. Propagates just means to continue. So each little point along the new wave is going to keep pushing out in a semicircular fashion, and that's why it's diffraction. It's the spreading of light, and form its own new little wave. And I did one more of those. So you could look at the same thing for something that's a point source. Oh, there's another one. Okay. So if I do a point source, so let's say instead of having a line of waves like you would see at the ocean, you might see those plane waves, kind of, if you're at the beach, those type of waves there. But a point source would be more like you drop a rock in a pond, that sort of a wave. So it's going to ripple out in a circle. So what you would see there is that here's the direction of my wave that I have here. I could have done it all the way around, but I just did it to the right. And I'm going to have a ripple that's continuing like the blue line there. And so just like on the plane wave, on the point source wave, I can say that there's a near infinite number of points along this blue wave that act as its own little semicircular point source. So what's going to happen is, here I chose 3, it's kind of close to infinite again, and I let each of them create its own little ripple pattern going out. So if I had enough of those, if they were all really, really close together and overlapping, they would form the next wave front, and that's the way that the wave propagates. So that's what Huygens' principle is. We don't do anything with it, we don't do any math with it or anything like that, but it's the idea. So that's how the wave is going to move as it continues. And I'm going to show you a little animation of this here on this applet. So here's an applet that shows us a wave that's being generated from a point source. In this case it's water. I could also do sound and light, and I might play with that a little bit as well. And I can adjust a lot of things about this. I can do the frequency for one thing, and as you do that you see that there's a pattern to the waves, and I think that's exactly what you would expect to see. Now if I add a barrier, I'm going to do a single slit barrier. I can move it over in front of where my water drips, and you're going to see that the water does come through, and then it starts creating that semicircular pattern. So if I change the slit width, it's a little wide right now. We can change it, that's a little hard to see. And you can see that pattern developing. I can change the frequency. And that's exactly what Huygens principle is. It's just, why is there that semicircular pattern? Why doesn't it just go straight through? Because if this were like, you know, a line of basketballs rolling towards the slit and one basketball got through, it would just keep rolling in a straight line and that's all you would see. So this is how a wave is different than a particle in its behavior, is that it has this idea of this behavior of diffraction, that it will bend when it goes around something. So that's all we're going to look at that for the moment, and we'll come back and look a little bit more at it here in a second. So actually I'll do that right now. So I'm going to add, instead of just one slit, see what happens when you add two slits. Now something kind of interesting happens. Instead of having a single semicircular pattern, you have what they call an interference pattern, because you have two semicircular patterns, one from each slit, and they're going to overlap with each other. And when they do that, it makes a little pattern. I'm going to try the light one. I think I like the light one just a little bit better. I don't know, maybe not. When I increase the amplitude, I'm just trying to make the light a little darker. Well, I don't know if I really like that much better, but you can see straight up the middle, those are areas of constructive interference where you have darker dark spots and lighter light spots. And then you have these fuzzy lines. Where these fuzzy lines are that's what's destructive interference. So we have lines for each one of them. So we'll go back then to our PowerPoint. I'll pause that and go back. And this is kind of the pattern that you get. This is called an interference pattern, where you have spots that interfere constructively and some that are destructively. So on this pattern, I can take a look at spots that are anything that's directly on, by the way, these lines, each line is a crest. So you have crest, crest, and right halfway in between the crest, that's considered a trough. So you have crest, trough, crest, trough. That's how to read these kind of pictures. The S1 is for source 1 and the S2 is for source 2. You only have interference when you have two sources that are interfering or overlapping with each other. So something we're going to look at here is from the three spots that I put on this graph, we're going to look and see whether those are areas of constructive or destructive interference. And there's two ways that we can do this. We can look at the path difference, and I'll talk about that more actually in the next video. The other thing that we can look at is the just the wave parts that overlap. So if I take a look at the orange one here, the orange one is on two crests because it's on a crest from S1 and a crest from S2. So crest, crest, that's constructive interference. The green one is going to be right in the middle. It's not on any crosses, so that's trough, trough. So that's going to be constructive interference. So if you have the same two wave parts on top of each other, it's constructive interference. So now if I look at the purple one, it's on a crest coming from S1 and a trough coming from S2. So crest, trough, that means it's going to be destructive interference. So you can look, just by looking at the wave parts, you can tell if it's constructive or destructive interference. But another thing that we'll look at here is the path difference. And we'll do calculations with the path difference on the next video, but we can look at basically what it is. So we're going to look at the difference in the number of waves if I start at S1 or if I start at S2. So for the orange one, if I start at S1, I count from the source, I'm going to do 1, 2 waves. So there's 2 waves to S1 and 1, 2, 3, 4, 5 from S2. So if I look at that, if I look at the difference in the number of waves, that tells me that there's 3 waves. And here's the trick. If I get a whole number when I count the number of waves difference, then it's going to be constructive interference. If I get a half number, then it's going to be destructive interference. So not even or odd, but it's got to be whole number or half number. Whole number constructive, half number destructive. So on the green one, if I count the green one, I start from S1 and I count 1, 2, 3, 4 and a half. So there's a half. And then I do S2, I count 1, 2, 3 and a half. Well, but because both of the paths have a half in it, the difference is still a whole number. So it's one wave, so it's constructive interference, which is what we expected from looking at the overlapping wave parts. From the purple one then, if I count from S1, I get 1, 2, 3, 4, and if I count from S2, I get 1.5. And we're not going to do any weird fractions, so go for whole or half numbers there, so don't say a third or anything like that. So if I look at that, I'm going to have 4 waves minus 1.5 waves, so that's 2.5 waves. So a difference of 2.5 waves means I have destructive interference. Okay, so let's take a look at this next thing. There's a nice way that you can look at on these interference patterns just by which you saw in the animation how there turns out to be